Start with partial derivatives again. And this time I cannot do the shortcut from my second example, because the function defined in two clauses. In the origin it is 0, in the outside the origin it's some formula. So we need to go by definition. We need to go by this line. And when we go by this line, this f of 0 is 0. Here I replace my function with only h here, y is 0. We end up with the expression like that. Do you know what's the limit of this expression? It's a one-dimensional example. It's the first year stuff. If somebody tells you, prove this limit, what would you do? Or just find the value for such limit, what would you do? Huh? Integrate? Who said that? You're on exam, you're facing the limit like that. You need to solve it, life or death. What do you do? Huh? L'Hopital, you said? Yeah, well, it's a very good, it's a choice students always make first. Yeah, you can do L'Hopital. You can do L'Hopital, the limit will be 0. But I'll do it differently, because I want to mention this inequality again, because inequality always, it's something underneath the limits. And I want you to see this once. It's not an easy inequality. It's not an easy. It is not as easy as the one I showed you for this sine function, where it was sine a on a take 1 absolute value less than a squared. This one a little bit more twisted, but that's the one which appears in many examples where you need to do something with limits with exponentials. So here it is. I call it a lemma as a statement. So I just separate statement. I'm not going to prove it, and you don't need to prove it. But if I have some limit questions with exponentials in the tutorials, I will put it next to it as a hint, and you feel free to use it. So it says this. For any integer, positive integer, there's always a constant bn. For every positive integer, there is a constant bn with such a property that exponential of this type never exceeds the power function of this type when a between 0 and 1. It's a formal statement, but listen how it sounds in the plain English description. The important part here, of course, the vicinity of the origin, when a approaches the origin, because when a approaches the origin, it's a typo here, it's supposed to be plus n. It's a typo, it's supposed to be plus n. When a approaches the origin, what happens with the exponential? If a goes to plus 0, to 0 from the positive side, what happens to the left-hand side of this inequality? What does it do? Go 0, that's right, because the negative part of the exponential graph, which decays to 0. What happens to the an? What happens to an? When a goes to 0. A power n for the positive n. I see some hesitation in class. So first it's 0, it's a power function. Take n equal 1, linear function. Where does it go? 0, right? The inequality says, in plain English, listen to this, exponential function decays much quicker than any power function. No matter how much you wind this power n, if you start pumping this n up, say take 10, 10,000, 10 millions, your power function will start entering 0 quicker and quicker, right? If you take the 10th power of 1/2, it will be 1 on a million already. And yet, exponential will still beat that eventually. That's what the inequality says. Exponential always decay faster than any power function, no matter how much you take, how large you take this power. And that's what we see here. This is the exponential, which is decaying, and that's the power function, which tries to beat that decay. And this never happens. Exponential always dominates any power function. That's why the limit is 0. So formally you can argue like that. If you take this lemma for n equal 1, just for n equal 1, then this exponential for n equal 1, you can by lemma, you can write up this inequality, right? You control this exponential by n is 1. That's why b1 here. And here my here will be absolute value of h squared times 1 negative 1, it will be this, if you do the arithmetic, I mean. H squared comes from this part of my lemma, and you just take 1 away because we have this extra factor. So if you use the lemma, you can write this, and it's a sandwich principle. This goes to 0. This is a 0. That's why the middle part also goes to 0. That's how you see this limit equals 0. Formally, by the lemma, sandwich principle. At this stage, you may say a L'Hopital rule is better. I accept that. It's a very algebraic way to argue limits. But it's just one piece of this argument. We will need this inequality again, and on that occasion, probably L'Hopital rule will, I don't know, we'll just see if L'Hopital works there as well. So, let's just move on. It's my second partial derivative. Similar argument, function actually symmetric in x and y. That's why second partial derivative will be 0 as well. The same argument works. Now I have a candidate for the L matrix. Now I have a candidate for the L matrix to check. So I take my Jacobian, which is trivially 0, 0 this time. That's my choice for L matrix. And again, I copy my line from the definition of differentiability. I'm going to test this limit. And this time, we hope we will succeed. Limit will exist. So again, as before, this is like that. This is like that. So I start my testing. I sub in what probably I scroll up too early. I sub in what I have for my components. This is just 0 this time, again, trivially. This is 0, right from here. All I have to substitute is this expression, and then the bottom, the denominator. So here's my substitution. Here's my substitution. Yeah, here it is. I need to convince you the limit is 0. Some of you may say, L'Hopital rule again. As a matter of fact, I can challenge you. Can you try L'Hopital rule? Even here, L'Hopital rule is not going to look as easy because derivatives, they don't look nice. But if you try L'Hopital here, that will be the killer. With the roots and exponentials and everything. And actually, I'm sorry, wait a sec. I'm taking this back actually. Because L'Hopital, it's a one-dimensional result. Here we have a function of 2 variables. Yeah. So I take it back. L'Hopital, we have to put it aside. That's right. L'Hopital doesn't help here. But my lemma, this inequality for the exponentials, it does help again. Because again, I can make a sandwich principle out of it. Look at this. If I take now as A in here, this expression in brackets, x squared plus y squared, and again, if I take n equal 1 in my lemma, that's what I'm writing. So I do the abbreviation, that's my g function. I use my lemma. So by this lemma, that's what I write. If I take in place of A this bracket, it comes out here as it is with n equal 1, and then I have to cancel one root because of the denominator. Here's my expression. It's again a clear case for the sandwich principle. When x, y goes to 0, it means that this number goes to 0. We have a sandwich principle, and that justifies the limit. Inequality